We have already seen that materials will deform under load, and that this deformation can be related to a material property known as stiffness. But how universal is the stiffness to a particular material? Is it possible that it can vary within a material or along different directions within a material? These are some very good questions, so let's see if we can come up with a hypothesis which provides a possible answer and design an experiment to test it. First, let's start with a hypothesis. I believe that material properties will not vary, so I will make the following hypothesis. Material properties, such as stiffness, are independent of direction within a material. It's not important to be correct with our hypothesis here. We just want to word it in a way that we can design a possible experiment to challenge it. So how can we test this hypothesis? The best way to test a hypothesis is to think of an experiment that would show us if our hypothesis is wrong. That may sound strange, but it's actually an important part of the scientific method. Only when we fail to disprove something can we hold it to be true. For our test, we want to see if the stiffness would change with direction within a material. So, we could take a piece of material and cut two rectangular specimens out of it, each cut out at a different angle. We could then load these specimens in tension, measuring their force deflection behavior. What would we see if our hypothesis was wrong? Well, this would mean that the stiffness of the material would be different in the two directions tested. We would see this by seeing a large difference in the slope of the force deflection curve of our experiment. Now that we have a concept for our test, let's see if we can carry it out. For this experiment, we are going to test two different materials: burlap, which is a fibrous material used for making things like potato sacks, and some cotton fabric used to make t-shirts. As in our experimental design, we will cut rectangular specimens from these materials, one at an angle of 0 degrees and the other at an angle of 45 degrees. Now that we have our specimens, let's go to our Delft Aerospace Structures and Materials lab to test them. For this test, we will use the tensile test machine shown here. This machine has sensors in it that can measure both the force and displacement as we run the tests. First, we will test the t-shirt material. Here you can see the footage of the t-shirt material side by side. As the test progresses, you can also see the force deflection curve being generated by the test setup. So what do we see? It seems that the slopes of the two curves are nearly the same. So this material is, in fact, supporting our hypothesis. But we shouldn't get too excited yet. The behavior of one material does not necessarily represent the behavior of all materials. So let's test our second material. Here you can see the footage of the burlap material side by side. As with the last test, we can also see the force displacement curves that go along with the tests. And it seems something is very different here. We can see that the deformation behavior of the 45-degree specimen is very different than the 0-degree specimen. We can see this both by the footage and by the slope of the force deflection curves. The material appears to be much more stiff in the 0-degree direction than in the 45-degree direction. The material properties are clearly different in different directions. So what can we conclude from our experiment? At first, we made the hypothesis that material properties are independent of direction within a material. But in our experiment, we found that although this is true for some materials, like the t-shirt material, it is certainly not true for all materials. Our hypothesis is thus proved wrong, at least for some of the time. Engineers are aware of these two different material conditions and have come up with terms to describe them. If the properties of a material are independent of direction, we call that material isotropic. If the properties are dependent on direction, then we call that material anisotropic. Anisotropic materials may sound strange and less useful than isotropic materials, but this isn't always the case. Anisotropic composite materials are being used more and more in aircraft, such as the Airbus A350, as they provide unique opportunities for design optimization that can make the aircraft even more efficient. Perhaps one day you'll design a new aircraft making use of anisotropic materials.